Hi, everyone. I'm Peter Naylor, a postdoctoral research in the high-dimensional statistical modeling team. And today I'm happy to present to you Boris Muzellec, a postdoctoral researcher in the Sierra team at INRIA. And today he's going to present some work he has done in optimal transport. So thank you very much, Boris, and you can do it.
Thank you, Peter, for the introduction. So today I'm going to present a work that I did with Adrien Vacher and François-Xavier Villard from Université Gustave Eiffel, and Alexandre Roudier and Francis Bach from INRIA and the Sierra team. So this work was published at the last COLD conference, and its topic is the how we can handle the curse of dimensionality in optimal transport using kernel methods. So I'm going to start with a quick introduction to optimal transport, and I'm going to explain how it is affected by the curse of dimensionality. Then I'm going to introduce the tools that we're going to use to try to alleviate this curse of dimensionality, which are namely kernel sum of squares. And then finally, in the last part, I'm going to wrap everything up and explain what we were able to obtain with our methods. Let us start with the introduction to optimal transport. So you know very well that in machine learning or data sciences, we often have to compare distributions. Okay, so in a typical setting, we might observe some data, which comes under the form of a discrete distribution, for instance, and we would like to fit a model over it, okay? And so we must find a way to compare the distributions to tell whether our parametric model is a good fit for discrete data or not. And so there are several ways of comparing distributions. So I'm going to argue that there are essentially two ways of comparing distributions. The first way is to compare them vertically. So this is what we do when we use the most popular divergences between distributions, for instance, the total variation distance, the Kullback-Leibler divergence, and so on. So essentially what we do is at each location, we look at the difference between the densities or the ratio of the densities, and then we turn them into a divergence, okay? So if you look closely, you can see that total variation, Kullback-Leibler, and F divergences in general, they all do that, okay? But what if we wanted to compare them horizontally, for instance, okay? Because if you take this example, then according to a Kullback-Leibler divergence, for instance, there will be quite difference because at each of the modes of the blue and the red distributions, the difference between the densities is quite high. But to us, it seems like they're very similar. We can see that they're just the same Gaussian has been shifted to the right or to the left. And so the hope is that if we could compare distributions horizontally, we might even be able to compare distributions that have disjoint supports, right? Which is not necessarily the case of so-called vertical divergences, because, for instance, the Kullback-Leibler divergence goes to infinity when the supports are disjoint, or the total variation distance plateaus to 1 if it's properly renormalized. And so this is essentially what optimal transport is about. So in this talk, I'm going to focus on Kantorovic's view of the problem, which was introduced in the 1940s. So let's say you have two probability distributions, and to give us an intuition, I'll focus on the case where the probability distributions are discrete. And I'm going to motivate optimal transport using an example from logistics, okay? So let's say that our distributions represent factories and stores. So each factory produces a certain quantity of goods, and each store requires a certain quantity of goods, okay? And so the total mass of goods from the factories and the stores must be equal, so they're normalized, okay? And what we would like to do is we would like to transport the goods from the factories to the stores according to some ground costs, which can be the cost of transporting, the cost of fuel that is required to transport each unit of good, okay? And so what optimal transport is about is trying to find the optimal allocation of goods from the factories to the stores that minimizes the total cost. And so if I come back to my mathematical framework, what I'm trying to do is I'm trying to find the coupling or the transportation plan and this transportation plan is just a joint measure over RD times RD, which has the right marginal, so mu and nu, that minimizes the total cost, okay, which is just the integral of this cost, the expectation of this cost over this transportation plan. Okay, and so if we take our cost function to be a distance to power p, this defines the Wasserstein distance, which is quite useful because it is actually a distance between probability distributions and not only in divergence. So it has all three metric actions. And so this was the discrete point of view, but it still works in the continuous point of view. And actually, if the distributions have smooth densities, then you can show that the optimal transportation plan, which was represented here, concentrates on the graph of a map, which is called the transportation map. Okay. But in this talk, I'm mainly going to focus on this point of view and actually on the dual point of view of this problem. So we're going to consider the case where the cost function is the squared Euclidean distance. And we're going to consider the dual formulation of the previous problem. Okay. So in the dual formulation, we're trying to maximize the integral of a potential against mu and another potential against nu under the global constraint that the cost function should be greater than the sum of those potentials at any points, any pair of points. So this seems a bit abstract, but we could still try to interpret it using a logistics interpretation. So let's come back to our factories and our stores. But this time we want to, we're going to ask a vendor or a logistician to do the delivery. And this vendor is going to charge us according to a certain pricing scheme. And he's going to charge us U of X, a price U of X for collecting each unit of good from a factory. And those factories are distributed along, according to mu. And he's going to charge V of Y for delivering each unit of good to the warehouses that are distributed according to nu. Okay, so of course, the vendor aims to maximize his profits. So he's trying to charge us as much as possible. But he cannot charge more than a given fair price or a market price that is encoded by this cost function. So if he picks up a unit of good at location X and delivers it at location Y, he cannot charge us more than this cost function here, because otherwise we wouldn't pay. For instance, we would think that the cost is is too much. And so this is this dual formulation that we're going to consider in the rest of the talk. Okay. So this was the introduction of well, the definition of optimal transport. The natural question is, well, can we do something with it? Because for now it's mathematical definitions under the form of optimization problems, but can we actually compute optimal transport? Well, if we take the easy case where the distributions are discrete, I'm not going to go into details, but you can convince yourself that optimal transport is equivalent to a linear program with linear constraints, and that it can be solved in time n cube log n if you have n points in each distributions. So it's already a bit costly, but it's something that you can solve exactly using linear programming. However, if your distributions are not discrete, and if they are densities, then there's in general no closed form or general method to solve optimal transport. There are some particular cases which limit closed forms, such as Gaussian measures, but in general, you cannot do anything. If you're in low dimensions, you can try to discretize the space. This is going to work in dimensions 2 or 3, but if you go higher dimensions, then you're not going to be able to do anything. And so this is a very tough case in which it's very hard to estimate optimal transport. So you might think that you could try to sample from mu and nu and estimate optimal transport from the samples, okay? So assume you can sample from mu and nu. You would build discrete distributions from mu and nu, and you could try to estimate the distance by taking the optimal transport distance between the discretized distributions, the empirical distributions, and comparing it to, and hoping that it converges to the actual distance. So actually it does converge to the actual distance, which is good news. But the bad news is that it does so exponentially slow with respect to the dimension. It converges in expectation at rate n to the -1 over d. So this rate can be slightly improved to n to the minus 2 over d, which has been shown by Linnaeus Shiza in 2020 under some mild assumptions. But there's nothing much more that you can do. It's still going to be plagued by the curse of dimensionality. And so let me try to give you an intuition of why this would be the case. So I'm going to focus on a setting in which mu is the uniform distribution over a hypercube. And the cost function is just going to be the Euclidean distance, not squared. And I'd like to see how the optimal transport distance between mu and its empirical counterpart behaves. So this is how optimal transport between mu and mu hat looks like. So each point in mu hat is going to be transported to a given region in the hypercube, okay? So those regions are actually, since mu is uniform, and they're actually Voronoi cells. And so each of those cells has a volume 1 over n because it's 1 divided by the number of points. And it has a radius, so this is super hand wavy, but try to imagine that they are balls and not Voronoi cells, then they would have like a radius or an average distance of n to the minus 1 over d. And so transporting each xi to its corresponding region ci costs this average distance, n to the minus 1 over d, times the weight of xi, which is 1 over n. And so the total cost is going to be the sum of those individual costs. And so we're going to get this n to the minus 1 over d, total cost. Okay. And so why should we care about this distance between mu and mu hat? Well, because you could try to, for instance, to estimate the distance between mu and nu. You can try to bound it from above using the fact that it is a distance using a triangle inequality, and you would get this greater to the n minus 1 over d rate. And so the way I've presented it here, it's an upper bound, but it's actually also a lower bound. You can show that there's nothing you can do even if you try to pick the samples not at random. If you have a discrete distribution, then you can change the constants, but the rates are still going to be n to the minus 1 over d, unless you make more assumptions. So can we do better? So Linnaeus has shown that if you assume that mu is different than nu, then on the mild assumptions, you get rates that are n to the minus 2 over d. So it's better, but still plagued by the curse of dimensionality. But thankfully, there's hope. Because over the past few years in the fundamental mathematics community, there's work that has been done on the specific case where mu and nu are assumed to have CM densities. So they have densities that are n times continuously differentiable and that are bounded away from 0 and have some assumptions on the supports. Then you can show that the transportation map, which is linked to the transportation plan, as I showed in the past few slides, is also very smooth. And so there's been works in the statistical community to try to derive the min-max estimation rates of optimal transport under those smoothness assumptions. And so, for instance, Hutter and Rigolet have shown that if the densities are CM, then you could estimate the map at this rate, which depends on the smoothness, and in which you can see goes to n to the minus 1 when the smoothness becomes infinite. And Will and Berthet have also shown similar rates for density estimators that go to the n to the minus 1 over 2, so square root of n when the smoothness goes to infinity. So compared to the plugin rates that are exponentially dependent on that dimension, those rates are fairly efficient. But the natural question is, well, are those theoretical, or can we try to implement those estimators? And it turns out that, well, in those two papers, there are no practically implementable algorithms. The first one is NP-hard to compute, and the second one still has exponential runtimes with respect to the dimensions. And so what we tried to do in our work is to find estimators that have rates that compare to those min-max rates, but that also have tractable, let's say, polynomial computational rates. And so what we try to do is to get, yes, a tractable and efficient estimator. And we started from this dual formulation. And so as we saw in the previous slide, we know that if mu and nu are smooth, then the potentials are going to be smooth as well, sorry. And so what we'd like to do is to find a way to represent the potentials u and v, and also to somehow represent this constraint function. So it's just this constraint that I've rewritten under this non-negative form. We would like to find a way to represent the potentials in this function here in a form that we can efficiently learn from samples. So for instance, we could try to learn the potentials as kernels, as functions in the RKHS, which causes no problem because we know that they're smooth. And we could try to do the same thing for the constraint function, but it has this additional constraint that it has to be non-negative, which is not straightforward to encode with the kernel methods. This is what we did in our work, and I'm going to explain how we encoded this function. And just a little teaser, what we obtain is an estimator OT hat, which has a rate that goes to 1 over square root of n when the smoothness goes to infinity, actually when it's bigger than 2D. And that can be computed to precision epsilon and time greater of n to the 3.5 log n over epsilon. So also as a disclaimer in this talk, I'm going only to consider the rates. So which means that the constants inside my greaters might still be exponential with respect to the dimension. I'm not going to go into the constants. I'm just going to focus on the rates. And this is what has been done in the rest of the literature as well. So the rates I've shown you in the previous slides also have hidden constants that are exponential in the dimension and which are inherent to optimal transport and cannot be beaten apparently. Okay. So at this point, if you have questions on the optimal transport part, maybe it would be the time because I'm going to switch to the part on the kernel sum of squares.
There was a question in the chat.
Okay, I cannot see the chat, so yeah. Please,
so I'll say it to you.
Okay.
So Anna Mattison asks, what is the reason Wasserstein distance was adopted instead of the Kurbach-Leibler or the other divergence?
So depending on your applications, for instance, anytime you have to compare distributions that have disjoint supports, then you cannot do so with the Kurbach-Leibler, right? Because if you have two Dirac measures, the Kurbach-Leibler distance between those is going to be infinite unless they're the same. Whereas the Wasserstein distance, for instance, is going to be equal to the Euclidean distance between the position of the Diracs, okay? So you can, in the case of Dirac measures, for instance, the Wasserstein distance is able to encode convergence of the supports to zero, to the same point. Whereas the Kurbach-Leibler divergence is not going to be able to do that. And this is important in some applications such as generative modeling, for instance, because let's say you have a network that tries to produce images and you'd like to quantify how far the distribution of images it produces is from the actual distribution, the natural distribution of images. Then if you use distances that cannot handle disjoint supports, then it's going to be very hard because if you generate things that are not images, then quantifying the distance between those things and true images is going to be very noisy. Whereas if you use the Wasserstein distance, then you can do it without any other issue. And also, so this is one reason. Another reason is that optimal transport arises naturally when you try to model certain things, where I gave an example of logistics, but also has applications to PDEs and the Fokker-Planck equations, and some natural phenomena in physics also behave like optimal transport. So there are theoretical reasons in statistical and data sciences to consider them, but there are also reasons in natural sciences.
Okay, thank you.
Okay.
There was another question from Wiping Liu. Are your estimation rates optimal? Is seem different from Philip's result?
Yeah, so I simplified. So if you compare to the paper, I simplified the bounds a little. So if M is greater than 2D, then our rates are optimal. But in the regime where M is smaller than 2D, so you're smooth, but not super smooth, we're not exactly optimal. We're slightly less optimal than, we're not optimal compared to the min-max rates. We're not too far, but we don't have exactly those rates. So the rates you should compare are those one, essentially. And you can see that when, yeah, M is bigger than 2D, then we match those rates. But before that, it's not exactly.
Thank you.
Okay. You're welcome.
Maybe you can continue.
Yeah. So okay. So now let me try to introduce the tools that we're going to use to encode this function. So we'd like to find a way to learn a function that is smooth and non-negative. Okay, and this is something we're going to try to do using RKHSs, which is not common when you try to learn functions with shape constraints, but I'm going to explain how we do it. So just a quick reminder. So RKHS is a Hilbert space of function from RD to, we're going to consider function from RD to R here, that has a reproducing property. So you can evaluate the value of a function G in this RKHS as an inner product in this RKHS with the so-called feature map phi of X. And it has a kernel, K of XX prime, that's easy to compute. And that can also be expressed as the inner product between the feature maps at the location X and X prime. So we're going to introduce a model for non-negative functions through so-called sum of squares. So let's consider a positive semi-definite operator. So if you're in finite dimension, this is just a positive semi-definite matrix, and in infinite dimensions in Hilbert space, it becomes a positive semi-definite operator. And we're going to write functions g of x under this form, so phi of x, inner product g phi of x. Okay, so since G is assumed to be positive semi-definite, this is necessarily non-negative. And another way to see this is if you perform an eigendecomposition of G under this so as this infinite, if you're in infinite dimensions, or finite if you're in finite dimensions, sum of eigenvalues lambda I that are positive times hi transpose, then you can rewrite this G of x here as the sum of the lambda I phi of x times hi squared. So this is just hi of x squared, according to the reproducing property. And so this is a model that was introduced by Marto Ferrer et al. In 2020. So I'll add the reference later on. And so we're going to try and write our function under this form. And first, I'm going to try to show that we can represent lots of non-negative function under this form. So with RKHSs, you have easy operations. You have the evaluation of a function G, you have the kernel, and you can also evaluate integrals as inner products. So an example of RKHS are Sobolev spaces, for instance. If you take various Sobolev spaces H of S with S greater than D over 2. So those are spaces where of functions that have square integrable derivatives up to order S. Then this defines a Sobolev space. And so we can see that with RKHSs in the classical model G of X equals G times phi of X, you can represent a very rich class of functions. And here in our example of optimal transport, we're interested in smooth functions, okay? So if we're sufficiently smooth, so greater than D over 2 smooth in Sobolev parameter, then we can write our functions as member of an RKHS. And in the specific example, we take the smoothness to be D over 2 plus 1 over 2. Then the kernel can be expressed, it corresponds to the classical exponential kernel. For other values of this parameter, it's slightly more complicated, but it still can be computed easily. So with classical RKHS, you can easily represent smooth functions. And so the natural question is what we can represent with kernel sum of squares in the same spaces. What we like about RKHS is that when we want to learn a problem from samples, which is expressed as some minimization problem of a functional of G in this RKHS evaluated as samples x1 to xn plus some regularization term, then you know that we have this finite dimensional representative theorem in Rn, which says that we can write the optimal value of G as a linear combination of the alpha I times K of xi. And so this problem of estimating a function in a big functional space becomes a problem of estimating a vector in Rn. And it would be nice if the same properties held for RKHS sum of squares. And this is what has been shown by Marteau-Ferré and co-authors in 2020. So we're going to focus on functions that can be written under this form. So they're going to be parameterized by a given positive operator. And they're going to be written as phi of x times a phi of x, which can equivalently be seen as writing G as a potentially infinite sum of squared functions, where those functions are taken is in this RKHS. And so you can see that everything here can be expressed using the kernel K, because those functions HI are in the RKHS, so they can also be expressed according to kernel K. And so under this representation, we can write sum of squares of Sobolev functions. Quite conveniently, we also have a representative theorem. So if we want to learn a problem that's based on samples, so we want to minimize the function of non-negative functions in this RKHS that are written as sum of squares. And if we regularize the trace of A, so which you can see is equal to the nuclear norm because A is constrained to be positive. And then we also have an equivalent representative theorem, which says that the optimal value G can be written as this time a bilinear combination of the kxi and kj. So it's this finite sum of bij, kxi, kj, where B, the great matrix B, has to be a positive semi-definite matrix of size n. Okay, so we can solve problems where we want to learn functions that are sum of squared Sobolev functions, for instance, based on finite number of samples as a problem, finite dimensional problem over positive semi-definite matrices. And this was used, for instance, for a non-convex optimization by Alessandro Rudi and Boris Marteau-Ferré as well, and Francis Bach in 2020. And so we're going to try and apply this model to optimal transport. So yeah, I'm going to switch to applying those tools to optimal transport. So I've been a bit fast, I think, on this part. So maybe if you have questions, I can take them now. No, okay.
Nothing in the chat. Yeah.
Okay, good. So let me try to summarize. So we consider we're trying to alleviate the curse of dimensionality and optimal transport from its dual formulation, and we know that the function u and v are going to be smooth. And we would like to represent the constraint function, which is non-negative by assumption, as a sum of squared smooth functions in the Sobolev space, for instance, for some positive A. So we know that they're smooth. Okay, so this is another viewpoint from the Philippis and Figali theorem that says that if mu and u have CM densities, that the optimal potential is CM plus 2. Previously, we saw the same result with the transportation map. So we know that G is going to be CM plus 2 and non-negative. And the question is that enough to write G as a sum of squares? And so it's not obvious because, for instance, you might think, okay, G is non-negative, it's smooth, so why don't I just take square root of G and say, okay, I write G as square root of D times square root of G? Well, as an example, if you take a smooth non-negative function, then it's not necessarily the case that it's going to admit a smooth square root, because square root of G might not be differentiable at the zeros of G. So for instance, if you take the function, the real valued functions that takes x and maps to x squared, then the square root of G, so square root of x squared, just absolute value of x, and this is not differentiable in 0. It's not always the case that you can. It might not be always the case that you can represent a smooth non-negative function as a square or even a sum of squares. And in the case of optimal transport, it's going to be, it appears to be even more difficult because not only do we have some zeros, but we have an infinite set of zeros that define a smooth manifold. So here I've represented the function g, the actual function g between, in the optimal transport problem between those two distributions. So this heat map represents the value of g, and the dotted line here are the zeros of g, and they correspond to the so-called transportation map, which solves the optimal transport problem. So the way you can read this is say, okay, this point here has to be to map to this point here in the optimal transport problem. So we're trying to write this function which has an infinite number of zeros as the sum of squared smooth functions. And it's not clear that we can do so for the reason that I just told you. And so the first result in our paper was to show that if our measures have smooth densities that are sufficiently smooth with respect to the dimension. So if we're in dimension D, we have to have smoothness at least d plus 1, otherwise our theorem does not apply. Then you can write our constraint function as the sum of exactly d squared smooth functions. And so as a consequence, if we take an RKHS that contains smooth functions, then there exists an operator of rank at most d, such as the constraint function can be written as a sum of squares. And so this is an extension of the results of Alessandro Rudi and co-authors that first considered this in the optimization setting where they have the finite number of zeros. And here in our case, we have an infinite number of zeros. And so, I'm not going to detail the proof because I don't think I'll have time, but the idea is that we use a reparameterization trick. So we take this function here and we reparameterize in y, for instance, to try and straighten the set of zeros. In doing so, we get a function which around its sets of zero behaves kind of like a quadratic, okay? Because around this line, the function is going to look like a tube. And so in that region, we're going to be able to write it as a sum of squares because it's reached just a quadratic. And in the regions where it's strictly positive, then writing it as a sum of squares causes no problem because we're strictly positive. So this is just an intuition of how we can prove this result. So if you have further question on that later, we can talk about it. But for now, I think I'm going to skip it. So the first, okay, so now we know that the optimal potentials from the regularity theory and optimal transport, we know that they're smooth, and so that they are in our RKHS. And we know that the constraint function, we've just proved that it could be written as a kernel sum of squares in this Sobori space HM. So now what can we do with that? So what we're going to do is we're going to take the original transport problem, which is here, and we're going to replace everything with, so we're going to replace this with a sum of squares, replace u and v with a function in RKHSS, and discretize everything. Okay, so we get this problem. So, and we also replace our distributions mu by their empirical counterpart. So what we would like to solve is this totally discretized version of the problem where instead of mu, we have the empirical version of mu. Instead of having the constraint function applied everywhere, we constrain it to be equal to a kernel sum of squares at some given location xi, yi that we've sampled. We take u and v to be in RKHSS, and we add two regularization terms because we're working in RKHS, and so we need to control the size of we need to control our functions to ensure that they have a finite expression. So we regularize the functions using the square norms and the sum of squares using the trace of the operator. So we're going to solve this problem, and the estimator we're going to consider is just the empirical counterpart of optimal transport, where we evaluate the estimated potential against the sampled measure mu, and same for v and nu hat. Okay, so now what we'll show is that this estimator has nice rates, and that this can be solved efficiently. So why do we do that? Well, what we've gained by replacing the constraint function, the inequality constraints with equality constraints as the kernel sum of squares are the so-called scattered data inequalities. So if you take, so the idea is that if you sample enough the space, if you cover enough the space, and you add smoothness constraints, then you enforce that your function cannot become too negative. So I'm going to define the so-called field distance, which is just the maximum distance between a point in our support and the sample point. Okay, and what Rudy and Wenlin have shown, so Wenlin and then Rudy, is that if you constrain a function, a smooth function, to be equal to a smooth sum of squares over a set of sample that covers well the space, then this function cannot become too negative, and the lower bound is a function of this field distance power m, which is the smoothness, minus d, the distance. And so to give you a quick intuition, let's say you have a function that you subsample, that's very smooth, and you subsample it at given points, and at those points it's 0, then the smoother this function is, then the less negative it can become between those points. Okay, so for instance, if it was just Lipschitz, then it could become as negative as n to minus n to the minus 1 over d in dimension d. But if it becomes smoother, then the smoother it is, the less negative it can become. And so the idea is that we're going to, what we just did here is that we relaxed in a way the problem because we subsampled the inequalities, but we replaced them by inequalities that are structured so that it cannot become too negative. And so we were able to leverage those inequalities to show that if we pick our regularization terms, lambda 1, lambda 2, suitably, so with rates that are roughly n to the minus n minus d to over 2d, then with probability at least 1 minus delta, when we go over a certain threshold of samples, then our estimator with a distance at most c lambda 2 to the optimal transport, the actual transport. And so we recovered the bounds that I just showed you a few slides ago. And in particular, if m is greater than 2d, then we get rates that are in 1 over square root of n. Okay, so we have rates that match the minimax rates when we're sufficiently smooth. And what's more, so this we already have, so we already knew. So it was shown by Uter and William Berthet, but what we didn't know is whether we could compute those estimators at a reasonable cost. And we showed that we could. So maybe don't look exactly at the problem, but we showed that this problem here, if you take its dual, it's just a quadratic objective over SDP constraints. And so it can be solved to precision epsilon in time n to the 3.5 log 1 over epsilon and in n square space. Okay, so what we have is we have estimators that are min-max, nearly min-max, at least when it's sufficiently smooth, but that can be solved and at polynomial rates. So I'm not going to say polynomial times because it's not, we still have a constant that depends exponential on the dimension, but we can solve it at polynomial rates and reasonable space. So to wrap up, what I've shown is in this talk, and what we've shown in this paper, is that we could have algorithms with polynomial rates that have to estimate the optimal transport distance between smooth distribution, whose corresponding estimator match the min-max sample bounds when the smoothness increases. But there are still a few limitations in future work that I've maybe not emphasized that much in the talk. So I've said that the constants are exponential in the dimension. And this is something that's that seems to be linked to the optimal transfer problem, and that seems to be very hard to overcome. One limitation that's particular to our estimator is that before our rates kick in, we have to have a threshold of sample n0 that can be very large, even in moderate dimension. In fact, it can be exponential in a dimension. So before we enjoy our rates, we have to sample enough points to cover our space, as I showed in the previous slide, so with the Wigley function. And possibly we might have to sample exponentially many points before we can enjoy our nice rates. So I gave orders for lambda1 and lambda2 in terms of the number of samples, but how to tune them in practice, not so clear. And in order to have efficient methods that we can use in practice, there's still some work to do in how to estimate those lambda1 and lambda2. And finally, remaining limitation is, could we find faster algorithms, maybe at the price of doing approximation? Because so we have methods that scale n to the 3.5, but this can quickly blow up, especially given that theoretically, at least, we need exponentially many samples before we can have nice rates. And this is still way slower than something that I did not talk about, but which you might know about, which is entropic regularization for optimal transport and synchron distances. So those synchron distances are approximations of the optimal transport distance, and in general, they do not converge to optimal transport distance unless you fine-tune the parameter well. But those methods that are used are quite prevalent in the machine learning community nowadays, because they're very efficient to implement. And so the question is, well, is there a hope that we could somehow bridge the gap between our estimators and those entropic regularized methods, or not? So this is something that we like to investigate in the future. So yeah, once again, so those results that I've presented have been published in the core 2021 papers. And so yeah, thank you for your attention, and I'm happy to take questions.
Thank you very much for that great talk, Boris. So there's some questions in the chat that I'll start. Why using the dual formulation can lead to possible kernel methods in polynomial time, but the primal version doesn't?
That's a good question. So essentially, the reason why we focus on the dual version is that, so Alessandro, Rudy, and Francis Beck had this intuition that because of this result, you could see kernel sum of squares as a way of turning infinite, so sets of infinite inequalities to finite equality constraints. So we had this so infinite set of inequalities, and we could turn it into a finite set of equalities at the price of some relaxation. We could quantify the gap using those scattered data inequalities. So this is why we focus on the dual. If you look at the primal, the problem is in the primal you have to model. This is the primal. In the primal, if you want to learn it from samples, you have to find a way to model those joint distributions over mu and nu from finite samples. So I'm absolutely not saying that it's impossible, but in our case, it was more straightforward to us to estimate it from the dual point of view than the primal, because we usually, I mean, at least in statistics and machine learning, it's usually easier to learn smooth function than to learn probability distributions, especially when they have marginal constraints. But I hope this answers your question. Definitely, it's probably not impossible to do something in the primal, but the dual seem more amendable in our case.
Okay, thank you. There's another question from Junhan. how do you define smoothness indefinitely differentiable?
Okay, so the smoothness we define is, okay, so so in the talk, I focused on CM functions. So there are functions that are m times differentiable, and the last derivative has to be Lipschitz, I think. So this is what I referred to as smoothness. But in the paper, you replace CM with HM, so functions that are in the subway space with parameter m, which means that they have derivatives that are square integrable up to order m, and well, actually up to adding 1 to m, so m becomes m plus 1. Those two notions are nearly equivalent because we focus on sets that have Lipschitz boundaries that are convex and compact. So if you're square integrable, then you also have up to adding 1 to the smoothness, you also have Lipschitz derivatives. So this is the notion of smoothness we focused on, and the reason we chose it is, well, because it matches the results from the regularity theory of optimal transfer. Those are the things we use to show that we could have a decomposition as a smooth sum of squares.
Can I just add a follow-up question to that? Is it essential to have, I mean, is it reasonable to all these smoothness conditions?
Reasonable to what?
Is it reasonable to have all these smoothness conditions?
Okay, so
in practice?
This is something. Okay, so in practice, it depends really on the. I mean, I have no general answer for that. It's. I mean, usually, like you have. If you assume, for instance, that your distributions have parametric models, and many parametric models for distributions are super smooth. Like if you take Gaussian, it's infinitely smooth, even though it doesn't have a compact support. But if you restrict it, so of course, well, essentially, so this is super hand wavy, but in my opinion, usually in practice, people focus either on cases where everything is discrete, because then they can do everything efficiently with computers. In that case, you don't really need those estimation methods because everything can be done in closed form, even though it's already a bit expensive. But right. And if you go to the regime where distributions are not discrete, but you assume that they have densities, usually you assume also that they have smooth densities because you have some parametric model in mind. And so in that case, it doesn't seem unreasonable. One thing we could do, so we didn't do it in the paper, but this could also be some future work. So in the case of in the paper on optimization by Alessandro Rudi and co-authors, they gave some rates of estimation when you use, so they show what happens if you take a model that is too smooth for your distributions, and you show that you do not have optimal rates, but you still have nice rates. So for instance, if we have densities that are CM, but we use sum of squares that are Cm prime with m prime greater than m, then we would be able to quantify what we lose by taking two smooth functions. So you try to approximate non-smooth function with smooth functions. So obviously it's going to be a little problem, but if you take many of them, then you can do something. So, but yeah, this is a question for future work.
Oh, very interesting. So there's 3 more questions, but I might ask the one on smoothness before because we're on that theme.
Okay.
Anna Mathisen asked, why is the leverage smoothness able to degrade the dimension?
Well, intuitively, if you add smoothness, you add constraints on how the true potentials can behave, right? So this is what I've tried to show, for instance, in with this wiggly line. So the smoother your function, the less wildly they can behave. And so, well, this is something I think is quite classical in the kernel literature, which is that if you try to estimate functions, then you in dimension D, and if you assume that they're smooth, if you pick your kernel well, you're going to get rates that are in the n to the minus something m over d. Usually it's something you get something like this. So usually the smoothness is able to somehow compensate for the dimension, because when the dimension increases, of course your functions have more space to behave. But if you add smoothing constraints, then they cannot do things too wild. And so in our case, for instance, the smoothness kicks in those bounds. So we say that the smoother the function when it's constrained to be non-negative on a subsampled set, then the less negative it can become outside of this set. So that's the first part where it kicks in, and the second part is just in the rate of no, sorry, no, yeah, that's the main point where we use the smoothness.
Okay, thanks. There's 2 more questions. Are there so Alain Matisson still? Are there any ideas how to tune lambda 1 and lambda 2 efficiently?
Yeah, that's a super tough question. So we have so there's a big hindrance in our problem is that so this thing here, our estimator, we cannot tell whether it's going to overshoot or undershoot optimal transport. We might get a value that's bigger than the true value, or a value that's smaller than true value. So it's hard to tell whether if we have a good lambda 1 or lambda 2. Because, for instance, if you do optimization, when you do optimization, you try to go lower, and if you use several values, well, you would pick the one that just corresponds to the lowest values you get, because you're trying to minimize. In our case, we don't know where we go. So we are currently writing a follow-up work of this, where we give a heuristic for estimating lambda 1 and lambda 2. And to give you an idea, the idea is that from the potentials mu hat and v hat that we estimate, we try to estimate a candidate transportation map, and we assess how well it transports the samples, okay? And so we try to quantify how well this estimated transport map transports the samples, and we pick the lambda 1 and lambda 2 for which the transport, this estimated transport is the best. So this is something that can be used then to perform a grid search, for instance, over lambda 1 and lambda 2. Of course, this is already very costly, grid search, because we've seen that the problem is already costly in itself. So if you have to try many values of lambda 1 and lambda 2, it's even worse. But how to pick lambda 1 or lambda 2 maybe adaptively is a big question that we're going to have to answer if we want to turn our methods into something that's efficient and that can be used in practice and not just something theoretical. So yeah, I have no clever ideas right now, but it's something that we're looking into.
What is the complexity?
So the complexity of solving this problem here is this n to the 3.5.
Sorry.
And I was just saying that for now, we don't know, we don't have anything much better than doing a grid search over lambda 1 and lambda 2 and applying some heuristic criteria that seem to work quite well in practice to pick the lambda 1 and lambda 2 we want from the grid. But so essentially what we're doing right now is that we're doing grid search over a problem that's already quite expensive. So if we could find a way of adaptively tuning lambda 1 and lambda 2, that would be great. Because what we'd observed in practice is that even though we have some statistical rates for lambda 1 and lambda 2, usually in practice, they seem to be quite pessimistic. And it's, we haven't found those rates very helpful from a practical point of view to fit lambda 1 and lambda 2. Yeah.
Okay, thank you. So there's also a message from Tamli. Thank you for the interesting talk. May you give some intuition behind the regularization term trace of A, and what is its formulation? What's its role in the formulation?
So, so the formulation trace of A. Okay. So the reason why we have this regularization term is to get the, so there's several reasons. One of them is to get this finite dimensional representative theorem. Because if we don't add regularization, then same as in kernel methods, then we cannot have a finite formulation. The second reason is that this regularization term plays a role in the bounds we get, because here I've written that this epsilon here is proportional to this the field distance, but there's also a constant here that depends on a norm, some like derivative norm of this function here, and that we can relate to the trace. However, we could have picked other regularization term than the trace. So here we have, we're considering PSD matrices, PSD operators and matrices. The trace is equivalent to the square norm, to the nuclear norm, sorry. But we could get similar algorithms and bounds using a square norm penalty, for instance, or any spectral norm that constrains the eigenvalues. The idea is that same as in optimization of vectors, if you use a trace or nuclear norm, you're going to encourage solutions that are sparse, meaning low rank. Whereas when you use square norm, you're going to encourage solutions that are not necessarily sparse, but have small square norms. So if you want to have more material on that, you can look at Ulysse Martos-Ferré NeurIPS 2020 paper, which describes which extends this result to other norms than just the trace norm.
Okay, thank you. So maybe one more question. What kinds of problems to solve would this technique be useful for, from Adam?
So that's a good question. So this work was so yeah, we had more like theoretical questions in mind when we approached this work. But the question being, okay, we have so those min-max estimators. Can we also implement them? So I'd say essentially they're useful if you have two distributions and you want to quantify how far they are in the optimal transport distance. So an example, for instance, let's say you have two distributions and you have to be able to sample from them. For instance, an application could be like you have two models that are generative models. For instance, you can sample from them, and you would like to know whether or not they sample from the same distribution. In that case, you would probably use other divergences, such as MMD, because they're better behave from samples. So to be honest, like at the top of my mind, I don't have any example where it's absolutely crucial that you use the optimal transport distance between smooth distributions. You could use some other distributions. It's more like an answer to, so over the past few years, the optimal transport distance has been used, has been more and more popular in machine learning applications. Some of them are inherently discrete, so this statistical complexity question does not arise, but some of them are not, and people seem to have good results using methods that, from a statistical theory perspective, should not be the case, because it should be plagued by the curse of dimension. And so from my point of view, this work is part of a general trend where we try to understand what are the inherent limits of using optimal transport in statistical science, in statistical theory, or no, sorry, in statistics and then machine learning. But for now, of course, if your goal is just to estimate some kind of distance between two continuous distributions that might have disjoint support, that you would not use this estimator because for now it's too expensive. you would use something like MMD or synchronous distances, which scale better.
Okay, thank you very much. I think it's been a whole hour now, so I mean, we would like to thank you again for speaking today.
Thanks again for the invitation. If you have if you're interested in this work or you have any questions, so there's our cool paper. We're working on a follow-up, but if you have further question that pop up, then please send an email or reach out.
Okay. Yeah, thanks for the Peter and Boris for the it's really nice seminar. A lot of questions and it's very fantastic talk.